15 overlooked stones hiding future billion-dollar gem discoveries. Beneath the world's most ordinary rocks lie clues to discoveries worth billions, quiet minerals that most people overlook. Yet each one marks the boundary of something extraordinary. Hidden chambers of ancient heat, forgotten belts of metamorphic pressure, and even the deep conduits that once carried treasures upward from the mantle. Tonight, 15 of these forgotten stones will rewrite what we think we know about value. Most are subtle, some are deceptive, and one, ranked first, is so rare, so silent, so chemically unlikely that its very existence hints at a geological event the Earth will never perform again. Don't forget to press and hold that like button, leave a comment, and hit subscribe before we begin. Ranked 15th, Vesuvianite, the misread mineral that whispered of hidden skarn wealth. For much of modern mining history, Vesuvianite was treated exactly like that. Visual noise. When veins of copper were logged, assay reports only mentioned grades of metal. When skarn deposits of zinc and lead were mapped, surveyors traced ore bodies and faults, not the small, blocky crystals trapped in their walls. Vesuvianite was collected as a curiosity, cut occasionally for jewelry, but rarely taken seriously. It never set records at auction. It never made headlines. Yet those modest crystals form under a very precise set of conditions. They do not appear just anywhere. Vesuvianite grows where molten rock forces itself into carbonate beds, where magma and limestone are crushed together under heat and pressure intense enough to rewrite the chemistry of an entire hillside. The result is skarn, a hard, altered shell around an intrusion, often charged with metal sulfides, gold, copper, zinc, sometimes tungsten or molybdenum. The heavy elements that power grids, wire cities, and anchor global trade. In that harsh contact zone, Vesuvianite is one of the first minerals to crystallize as silicate, calcium, and volatiles recombine. It becomes a kind of geological handwriting on the wall, spelling out one message in the language of crystals. The system here was hot enough, reactive enough, and chemically fertile enough to build ore. Only in the last few decades has that handwriting been read correctly. Remote valleys once dismissed as exhausted have been revisited with modern tools. On satellite imagery, subtle rings of altered rock traced around old intrusions match the scattered reports of Vesuvianite from generations past. In the field, geologists follow the pale green and honey-brown crystals along cliffs and road cuts, then drill beneath them. Some of those holes have punched into new zones of metal, extensions of known deposits, and in a few cases, entirely new bodies of ore. The revelation is simple and yet quietly radical. Vesuvianite was never a mere passenger. It was a witness. Where it appears in abundance, with the right companions and textures, it can mark the outer skin of skarn systems still underexplored. Systems large enough in a resource-hungry century to be measured not in millions, but in billions of dollars. In museums, Vesuvianite still sits on lower shelves, overshadowed by emerald and sapphire. Its luster is modest, its faceting unremarkable. But to those who now read rocks as maps, these crystals have changed meaning. Each prism is no longer just a specimen. It is a pointer, a hint that the real treasure may lie deeper, just beyond the last tunnel, just outside the last contour line drawn on an old paper map. Misjudged as decorative, marginalized in textbooks, Vesuvianite is being written back into the story of discovery, not as the prize at the end, but as the quiet guide at the beginning. And wherever that guide stands in the rock, other, more valuable secrets may be waiting below. As the overlooked stone finally steps into focus, another mineral waits in the wings, one whose razor-thin blades and precise geometry do not shout, but measure. That stone is Axinite. Ranked 14th. Axinite, the crystal engineered by pressure, guiding the hunt for lithium-bearing depths. In the geometry of minerals, few stones carry a sense of deliberate design. Axinite is one of them. Its blades taper to knife-thin edges, crossing and fanning like the ribs of an ancient mechanical instrument. When light touches its surface, it does not glow. It scans, moving across the striations with a clinical exactness that feels less like ornament and more like measurement. Axinite behaves as if nature drafted it, line by line, with the discipline of an architect who tolerates no deviation. This discipline is not aesthetic. It is chemical. Axinite forms only when temperature and pressure align in a narrow corridor and when calcium, aluminum, boron, and iron negotiate a fragile truce inside metamorphic rock. A few degrees too much heat, and the structure collapses into something common. A few ions misplaced, and the crystal loses the tension that gives it shape. Axinite is not merely rare, it is improbable, an outcome that requires the Earth to strike a balance so precise that each crystal becomes a diagnostic tool. And that is exactly how modern field geologists treat it. In regions where pegmatites rich in lithium and cesium cut through metamorphic belts, small clusters of axinite sometimes appear where no gemstone hunter would bother looking. The untrained eye sees brownish-violet shards lying in talus, easily dismissed. But the trained eye sees a vector, a marker. Because axinite does not grow on the fringes of chaos, it marks the transition zones, the narrow spaces where the chemistry of deep crustal fluids shifts from ordinary silicates to the more exotic species that accompany rare metals. Lithium, the soft metal powering the global shift to electrification, rarely reveals itself directly. It hides in pockets of pegmatite, veins formed from the final, fractionated breath of a cooling magma chamber. Those pockets rarely sit at the surface, but the thermal gradients that produce them also produce axinite. A handful of blades on a ridge, a small fan of crystals in a road cut, a few splinters trapped in schist. Each is a coordinate in a larger equation. Teams mapping for future battery metal deposits now use axinite the way navigators once used stars, not as destinations, but as fixed points in a drifting landscape. Where axinite displays an iron-rich signature, the pegmatitic fluids are likely more evolved. Where manganese dominates, the system may have cooled too quickly. The ratio tells a story of depth. The zoning reveals the direction of fluid flow. The edges record the cooling rate of a rock body buried long ago beneath a mountain now gone. The crystal becomes a transcript. In core samples, axinite can indicate the proximity of the fertile zone, the area where lithium-bearing minerals may thicken. In surface mapping, it marks the edge of metamorphic aureoles that wrap around granite bodies like halos. And in a few historic cases, axinite's presence predicted lithium deposits that would later become essential to entire industries. Yet axinite has no need for spectacle. Its beauty is almost accidental, its purpose unspoken. It lies in scree slopes and forest floors, enfolding metamorphic terrains where most stones pass without remark. But its very existence is proof that nature once held the conditions steady: temperature, pressure, chemistry, time, long enough to write a crystalline signature of astonishing accuracy. And for those who can read that signature, axinite is not an accessory mineral. It is a coordinate system waiting to be followed. From this symmetry of blades and ratios, the path bends toward a stone, bound not to geometry, but to memory. Maw Sit Sit, the green-black keeper of an older legacy. Ranked 13th, Maw Sit Sit, the ancestral greenstone, marking the hidden borders of jade-bearing earth. Long before mineralogy gave it a classification, Maw Sit Sit served as an emblem of continuity for the Shan communities. Worn in amulets, carved into small guardians, it was believed to echo the forests and monsoon rains of their homeland. In temples, monks placed pieces of Maw Sit Sit beside offerings of rice and oil, not for its value, but for its connection to land and ancestry. It was a stone that held place, literally and symbolically. But when the modern gemstone trade arrived, Maw Sit Sit slipped out of significance. Buyers wanted jadeite's translucence, its saturated emerald tones, its prestige. Maw Sit Sit's opaque mottled surface was too humble, too uneven. It was classified as decorative stone, sold by weight, not by story. Export documents listed it in small print, while jadeite climbed to the top of global auctions. A lineage nearly 5,000 years old was reduced to an afterthought. Yet beneath that quiet veneer lies its true legacy. Maw Sit Sit forms in high-pressure metamorphic belts, the same geological arenas that create jadeite. These belts are complex and rarely well mapped. They twist through mountainous terrain, buried under landslides, jungles, and political silence. In such terrain, Maw Sit Sit becomes more than a mineral. It becomes a marker, an indicator that the deeper, denser, jadeite-bearing zones are close. For geologists, it is a signpost pointing toward the heart of a system that still contains uncharted pockets of jade, some untouched since antiquity. When Maw Sit Sit appears in stream gravels or on the flanks of landslides, it hints at a buried architecture of rock, slabs pushed upward by tectonic collisions, compressed into layers that once reached temperatures and pressures near the limits of life. Within those layers may still lie jadeite chambers that escape the historical mining booms. Some may be vast, some may never have been disturbed. In a region where jade has shaped dynasties and economies, the discovery of a new chamber could shift the global gemstone axis. Modern surveys in Myanmar's northern tracts have documented Maw Sit Sit in places once assumed barren of jade potential. Its chemistry and texture, chromium-rich greens, fibrous intergrowths, tell geologists where the metamorphic gradients tighten, where the rock begins to remember the pressures that form jade. In those memories lies the next frontier of exploration. Thus, Maw Sit Sit's legacy expands. It is still the stone of amulets and monks, still bound to the cultural heartbeat of its homeland. But now it also stands as an archaeological key to the Earth's interior, a bridge between the oldest beliefs and the newest surveys, between folklore and billion-dollar futures. What was once dismissed as lesser jade now charts the map toward jadeite deposits that may rewrite the economics of an entire region. Maw Sit Sit carries no brilliance, no translucence, no theatrical beauty, only the quiet endurance of a stone that has walked beside humanity for centuries. And as it passes the baton in this documentary countdown, it leads toward a mineral shaped not by legacy, but by fire. Bytownite Sunstone, born from the volatile breaths of volcanic fields. Ranked 12th, Bytownite Sunstone. The volcanic memory stone, marking the path of unfinished magma. Bytownite Sunstone, subtle at first glance, pale gold to honey yellow, does not announce itself with the theatrical glow of labradorite or the bold scattering of Oregon sunstone. Its light runs deeper, like embers trapped beneath frost. To understand it, one must follow its origin rather than its surface. Its story begins in basaltic magma chambers, where temperatures exceed 1,000 degrees and the chemical broth of molten rock is still undecided. In these chambers, plagioclase crystals begin to form early, sodium and calcium aligning into fragile lattices that will become the backbone of sunstone. But for bytownite, the ratio tilts heavily toward calcium, a signature of magma rising fast from mantle depths, carrying its original chemistry almost unchanged. As the magma ascends and slows in the crust, impurities, tiny flecks of copper, hematite, goethite, hover and drift through molten liquid. In most volcanic systems, they are too diffuse to matter, but in a handful of rare environments, the cooling curve hits a precise slope, slow enough to allow the metal inclusions to align, but fast enough to preserve their metallic sheen. Layer upon layer of plagioclase grows over these flecks, sealing them inside the crystal. When sunlight moves across their surfaces, the inclusions scatter it into shifting currents of orange gold, an internal sunrise locked beneath the lattice. This phenomenon, eventurescence, is familiar in feldspar, but bytownite sunstone forms under more volatile conditions. It traces the edges of volcanic fields that have not fully revealed themselves, fields whose magma chambers cooled unevenly, leaving pockets of volatile-rich melt deeper down. In these places, bytownite becomes a geological breadcrumb, a sign that the eruptive story is unfinished. For geologists mapping the future of gemstone exploration, bytownite sunstone is an atmospheric clue. It signals the presence of basalt flows young enough to preserve trace elements, yet old enough to have fractured and weathered into accessible layers. Beneath those flows may lie the truly valuable zones, pockets where copper-bearing feldspar grows thick and clean, or where gas-rich cavities host mineral species not yet described. In several regions, the Deccan Traps, the Basin and Range, the volcanic arcs of East Africa, Bytownite has appeared at the margins of terrains that remain underexplored. In each case, its chemistry has pointed toward reservoirs of magma that cooled in the stages rather than all at once. Such reservoirs are exactly the type capable of producing large, undiscovered sunstone fields. Fields that, if tapped, could reshape the supply of colored feldspar and reveal new gemstone variants hidden in dark basalt for millions of years. To most gemstone dealers, Bytownite Sunstone remains a quiet curiosity, pleasant, warm, unassuming. But its true importance is not in how it looks, it is in what its structure remembers. The thickness of its lamellae, the orientation of its inclusions, the chemical profile of its feldspar layers, they record the breath of a magma chamber long vanished. Bytownite Sunstone is not a product. It is a trace, a remnant of volcanic genesis that points to deeper origins, deeper heat, deeper potential. And in the world of gemstone discovery, few signs are as valuable as a mineral that remembers where the fire last moved. As the glow fades and the basalt fields fall behind, the journey turns toward a stone shaped not by flame, but by anomaly. Hackmanite, the mineral that remembers light itself. Ranked 11th. Hackmanite, the color-shifting anomaly, marking Earth's hidden rare element systems. In a world where minerals obey quiet rules, crystallizing as chemistry dictates, reflecting light as physics prescribes, Hackmanite stands as an elegant contradiction. Under daylight, it may appear pale, a lilac haze, a muted grayish violet, a soft blue faint enough to be overlooked in a drawer of rough stones. Yet once it falls into darkness and returns to light, its color shifts, deepens, intensifies, as though the stone has awakened with a memory it should not possess. This phenomenon, tenebrescence, is so rare in nature that its presence borders on the improbable. A mineral should not store darkness. It should not remember the absence of light. And yet Hackmanite does, trapping electrons within tiny lattice defects. Release them, and the stone rewrites its own color. No other gemstone offers such a quiet defiance of the expected laws of optics. But Hackmanite's anomaly extends far deeper than its color-changing behavior. The conditions required to create it belong to a narrow and volatile corner of geology. Alkali igneous complexes, places where sodium-rich magma interacts with evaporitic sediments. These complexes form in only a few regions on Earth. Arctic terrains, continental rifts, deserts where ancient seas once dried into crystalline beds. Here chemistry behaves unpredictably. Elements cluster in ways that seem accidental, yet yield minerals crucial to the modern world. Hackmanite becomes the doorframe to this world. Its presence suggests that beneath the surface lie rare earth elements, Ariadne, the metals that drive the engines of the 21st century. Neodymium for wind turbines, dysprosium for high-performance magnets, terbium for aerospace composites. These elements never present themselves plainly. They hide in chemical shadows, scattered across complex igneous systems. But where Hackmanite forms, there is often a deeper igneous story, one rich in the light, flexible, technologically vital metals that power entire industries. In northern Greenland, samples of Hackmanite retrieved from frost-riven cliffs corresponded with rifts containing REE-enriched pegmatite swarms. In Afghanistan's dry interior, local miners once dismissed soft blue nodules as worthless, until researchers traced them to a deeper intrusive complex laden with rare metals. In Canada, Hackmanite's tenebrescence aligned with geophysical anomalies that later revealed a resource belt still being assessed for global-scale extraction. Everywhere Hackmanite appears, it signals something unusual, a chemistry that should not converge naturally, yet somehow did. A geological stage set for deposits whose economic value will multiply as technology demands more of what the planet produces least. And there is another layer to its anomaly. Hackmanite ages strangely. Leave it in sunlight too long, and its color memory fades. Tuck it away, and it strengthens again. This reversible instability is not a flaw. It is a clue. It mirrors the instability of the magmatic environments that create it. Hot, shifting, chemically restless zones where REE concentrate, disperse, and reconverge through time. Each shift in Hackmanite's color becomes a metaphor for the ground beneath it, territory that changes character with temperature, pressure, and tectonic breath. In the language of minerals, Hackmanite is an outlier, a statistical impossibility crystallized into matter, a stone whose beauty lies not in its hue, but in the way that hue refuses to behave. For explorers, it is the anomaly that matters most, because in fields where discovery depends on reading disturbances in the pattern, nothing is more valuable than a stone that breaks the rules. And as this anomaly closes its chapter, the story turns toward a mineral shaped not by memory, but by consequence. Hemimorphite, the quiet herald of deeper metallic histories. Ranked 10th, Hemimorphite, the pale blue witness to centuries of wealth, ruin, and buried silver frontiers. Hemimorphite forms in the exposed upper shells of zinc-lead-silver systems, systems that once fueled ancient trade routes and later powered industrial revolutions. These ore bodies, born from hydrothermal fluids coursing through carbonate rock, often left behind cavernous voids threaded with smithsonite, cerussite, and the airy blue veils of hemimorphite. Where the mineral appears today is not arbitrary. It maps the remnants of deposits that sustained empires, collapsed markets, and altered landscapes. Historically, its presence signaled both prosperity and cost. In Europe, where medieval miners carved deep into the earth for zinc and lead, hemimorphite coated the abandoned chambers like ghostly lace, an after-image of extraction. In Asia, it lined the entrances of forgotten shafts once worked by hand, where workers carried ore to the surface in baskets, unaware that the shimmering blue crusts above them foretold both wealth and hazard. And in the American West, hemimorphite often marked the boundaries of silver districts that rose swiftly, then sank into silence as the veins ran dry. But in the 21st century, hemimorphite has taken on a new significance. Modern exploration teams follow the mineral not for its value, but for its predictive power. Its chemistry reveals oxidation states, its textures record the path of fluids, its distribution reflects the geometry of ore bodies that extend far deeper than early miners ever reached. With satellite topographic models and deep penetration geophysics, hemimorphite becomes a precise indicator of where untouched material may remain. Zones too deep for ancient tools, too complex for early prospectors, but now within reach of advanced methods. Yet its appearance also raises questions. Every region crowned with hemimorphite sits at the intersection of opportunity and aftermath. Extractive histories left tailings rich in heavy metals, streams tinted by mineral runoff, forests thinned by smelter fumes. The mineral, quiet and beautiful, stands above landscapes shaped by generations who paid the price for progress long before environmental language existed. Thus, each new discovery near hemimorphite demands a choice. Should the buried ore, worth billions in modern silver, zinc, and critical metals, be approached with renewed extraction, or should the land be allowed to rest? Should the mineral guide a new era of responsible exploration, or has it already spoken enough with the consequences etched into the valleys below? In some countries, hemimorphite-bearing zones are now carefully measured, not mined. In others, advanced underground operations seek to extract remaining ore with minimal surface impact. And in a few remote regions, hemimorphite signals potential deposits untouched since antiquity, deposits whose economic weight, if unlocked, could reshape regional development. Hemimorphite is a reminder that geology does not act in isolation. Minerals outlast the societies that dig for them, bearing witness to choices made in search of profit or survival. Its delicate blue structures, grown from the oxidation of ancient ore bodies, stand at the frontier of both opportunity and responsibility. And as this stone of consequence steps aside, the narrative turns toward a mineral shaped by obsession, the indigo blue guide toward ruby-bearing belts, Dumortierite. Ranked 9th, Dumortierite, the indigo trace fueling a silent hunt for hidden ruby frontiers. Dumortierite, rich blue, violet, or dust-toned, is often mistaken for treated quartz or decorative lapidary stock. For decades, gemstone traders walked past it, focused instead on the more luminous species that commanded higher bids. To many, Dumortierite was a filler stone, pleasant, inexpensive, forgettable. But the earth keeps secrets unevenly, and sometimes the stones overlooked by traders become the ones geologists follow with unwavering intention. The revelation came quietly, not through a single discovery, but through a pattern observed by a new generation of field mineralogists. Wherever Dumortierite formed in narrow fibrous streaks within high-temperature metamorphic rocks, ruby-bearing structures tended to be close, sometimes within meters, sometimes within kilometers, but always within geological logic. Dumortierite marked the thermal gradients, the deformation zones, the pressure corridors where corundum could take shape in its rarest color. At first, only a handful of miners noticed. They mapped outcrops by hand, marking each Dumortierite vein with charcoal on their field sheets. When rubies surfaced downstream, unexpected, vivid, unmistakably fine, they retraced the water to its highland source and found the same indigo tracer weaving through schist. The connection held. Word spread quietly, not in auctions, not in trade expos, but in the hushed conversations of prospectors, the coded phrases of dealers, the cautious notes of geologists who knew what such a pattern could mean. Dumortierite, once sold in bags for beadmaking, suddenly gained a different significance. It was not the prize, it was the compass. As markets for fine ruby surged, driven by scarcity in Mogok, Myanmar, and tightening regulations in Mozambique, this compass became invaluable. Dumortierite veins in unexplored regions drew attention from private exploration firms. Investors requested samples. Universities funded structural mapping projects. On satellite imagery, even faint blue-bearing horizons were circled with careful anticipation. An obsession took form, not for Dumortierite itself, but for the promise it outlined. In some regions, artisanal miners began hoarding rough clasts of Dumortierite as if they were coordinates on a treasure map. They tracked downstream float minerals, plotted fracture trends, and dug exploratory pits where the blue mineral seemed thickest. In places where high-grade rubies later emerged, Dumortierite had already been present, quiet, consistent, unmistakably faithful to the pattern. Its appeal lies not in spectacle, but in reliability. Dumortierite records a thermal strain like a diary written under pressure. Its fibrous texture points to tectonic shear zones. Its coloration reflects the chromium-bearing fluids that also stain rubies. To those who know how to read metamorphic terrain, Dumortierite is the undercurrent beneath the gemstone world's most fevered pursuits. Today, its role is dual. To casual observers, it is still ornamental, pleasant enough, affordable, widely available. But to exploration teams, Dumortierite is cartography. It is the breadcrumb trail in a labyrinth of schist and gneiss. It is the mineral that outlines the shadow of wealth not yet discovered, the mineral that whispers of uncut ruby crystals still locked in mountain roots. Obsession thrives not where rarity glitters, but where patterns promise. Dumortierite has become the stone that sets those promises in motion. And as this fevered pursuit fades into the next chapter, the documentary descends into tension. The contested, high-stakes world surrounding Serendibite. Ranked 8th, Serendibite. The tension stone, marking the contested gateways to sapphire territory. Serendibite grows in deep, high-grade metamorphic corridors where pressures have folded the Earth's crust like pressed silk. These corridors are dangerous terrain. Twisted ridgelines, unpredictable slopes. Rocks fractured by both tectonics and time. But more importantly, they are the precursors to sapphire and spinal systems of exceptional quality. Wherever low-grade Serendibite appears, even in thin, nondescript bands, the subsurface chemistry tends to shift toward corundum stability fields. In simpler terms, Serendibite marks the doorway to sapphire country, and that doorway is contested. In Sri Lanka's Ratnapura district, early mineral survey teams noticed that shallow Serendibite veins ran parallel to old gem pits. The miners had followed the river gravels, not the bedrock. But the bedrock, laced with low-grade Serendibite, hinted that the richest pockets of blue and pink sapphire might still lie untouched in the hills. The discovery triggered silent maneuvering among local groups. Land leases changed hands. Private buyers from foreign markets drew maps in hotel rooms at night. Roadside pits appeared and vanished between sunrise and dusk. In Madagascar, the story sharpened. There, Serendibite streaks through remote highlands where law meets landscape in fragile balance. Along these belts, rival mining cooperatives monitor each other across valley floors. A single outcrop of Serendibite can spark a surge of prospectors armed with hand tools, GPS units, and unverified rumors. Reports have circulated, never confirmed, of districts where Serendibite-bearing zones triggered covert turf claims, negotiated under lantern light, enforced by local alliances rather than official boundaries. To companies studying the region through satellite imagery and structural models, Serendibite is a geological coordinate. But to the people living above it, the stone is something else. A potential shift in fortune, a signal that a buried sapphire pocket could recast the entire economy of a village. Low-grade Serendibite does not choose sides. It merely reflects a metamorphic event: high heat, high pressure, high deformation, conditions that also give rise to some of the world's most coveted gems. But its presence presses human ambitions against geological inevitabilities. It invites exploration deeper into territory where each step negotiates with risk. Landslides, collapsed tunnels, unstable slopes, competing claims, and the financial weight of what might be hidden just a few meters below. In these places, Serendibite is more than a mineral. It is the spark in dry grass. It is the tension line that runs beneath communities, companies, and cartographers alike. For while it has little monetary value on its own, the stone's true worth lies in the promise and peril of what follows it. Because where Serendibite thickens, where its bands tighten into dark seams, the subsurface often prepares to deliver its most coveted treasures: sapphires of striking saturation and spinels that glow like embers. As this contested mineral passes the torch, the narrative shifts toward a quieter guardian. Scapolite, the ancient waypoint linking human ritual with the architecture of ruby-bearing rock. Ranked 7th, Scapolite, the ancestral marble stone, tracing the forgotten boundaries of ruby country. Scapolite, creamy white, golden straw, or lilac at dusk, rarely draws attention. It lacks the clarity that collectors seek, and its luster, though warm, does not shout. Yet across the metamorphic belts of Afghanistan, Tanzania, and Myanmar, Scapolite endures as a kind of geological heirloom, passed down not through cultures, but through the slow rituals of the planet itself. Long before modern geology, ancient miners in Central Asia carved small talismans from Scapolite because it shaped easily and glowed softly under sun. They did not know its name. They did not need to. To them, it was simply a stone that lived where the mountains breathed. Archaeologists later found these carvings scattered along trade routes, sometimes abandoned in collapsed shrines or buried among beads and broken tools. Each piece marked a location where people once paused, rested, or prayed, small human ceremonies along the skin of the earth. But the stone they worked had another, deeper lineage. Scapolite forms in calc-silicate environments, chemical theaters forged when limestone encounters metamorphic heat intense enough to rewrite its structure. These same environments, rare, volatile, and profoundly altered, also give birth to ruby. Not every calc-silicate belt produces the Stone of Kings, but almost every ruby source on Earth whispers its presence through minerals like Scapolite. For modern mineralogists, Scapolite is not a charm, it is a signature. Its sodium-calcium chemistry records the passage of fluids enriched with aluminum and chromium, tracing the pathways that corundum needs to grow red. Its zoning patterns, those faint shifts in color and clarity, act like timestamps of metamorphic episodes that happened millions of years apart. Where Scapolite gathers in large coherent beds, the subsurface architecture often tightens into the pressure corridors that ruby prefers. In Tanzania's Winza Belt, veins of Scapolite were found long before any ruby surfaced. When rubies finally emerged in startling saturation, the old Scapolite layers revealed their quiet truth. They had been outlining the metamorphic domain all along. In Afghanistan, high on ridges carved by frost and silence, scapolite appears like faint chalk marks on marble, a gentle indication that deeper, chromium-charged pockets may lie below. Even in Myanmar, where ruby history runs deep, scapolite has reappeared in overshadowed zones that surveys once dismissed. It might yet redraw the boundaries of known ruby country, and so the mineral becomes a bridge between ancient hands that carved it for spiritual weight and modern hands that map it for geological insight. Scapolite keeps the memory of both kinds of seekers, those who look for meaning and those who look for structure. Its legacy is not loud, it is not dramatic. It moves like the mineral itself, slow, layered, resilient. A quiet companion to centuries of travelers, and now a quiet guide for the next chapter of exploration, where ruby-bearing marble may still hide untouched chambers of unimaginable value. As scapolite's pale glow fades into the metamorphic dark, the countdown turns toward a mineral shaped not by heritage, but by genesis pushed to extremes. Kornerupine, the survivor of heat and pressure that marks the edges of pegmatite wealth. Rank 6th, Kornerupine, the survivor stone, forged at the threshold of ancient pegmatite genesis. Kornerupine forms where temperatures soar beyond 700 degrees Celsius and pressures compress rock until its previous identity is erased. These are not environments of gentle transformation, but crucibles, zones where ancient sedimentary layers collide with granitic intrusions, where mineral bonds snap and reform with every tectonic heartbeat. Most minerals break under such regimes. Kornerupine endures. In these hostile theaters, its chemistry becomes a record of metamorphic genesis written under duress. Magnesium, aluminum, boron, each element must arrive at the right moment for the structure to assemble. Too much fluid and the lattice dissolves. Too little, and it never forms. Kornerupine is not the product of a single event. It is the survivor of a sequence, a mineral that passed through thresholds meant to erase it. This resilience is what draws the attention of explorers. Where Kornerupine appears in coherent bands, threaded through gneiss, streaked across schist, embedded in the flanks of ancient mountain roots, it marks the outer rim of pegmatite systems that cooled slowly enough to concentrate rare elements. These pegmatites are not the flashy pockets known to collectors. They are deeper, older, chemically richer. Within them, tourmaline grows in multicolored columns, chrysoberyl forms in honey-green clusters, and beryl develops into aquamarine or pale emerald. Kornerupine outlines this architecture like the margin of an illuminated manuscript. Each crystal acts as a marginal note, revealing how fluid pathways migrated, how heat pulsed through the crust, how pressure folded the rock into its current geometry. For geologists, it is less a gemstone and more a topographic whisper of where wealth may still lie concealed. In Madagascar's Zaramanga Belt, Kornerupine zones were initially dismissed as ornamental rock, but their distribution matched the metamorphic gradients that later revealed chrysoberyl pockets of startling clarity. In Tanzania, Kornerupine bearing horizons aligned with beryl-rich pegmatites hidden beneath layers of weathered soil. And in Sri Lanka, where centuries of mining have exhausted many surface deposits, Kornerupine veins still trace the boundary of deep-seated structures that may hold fresh discoveries. Its presence is reliable because its genesis is unforgiving. Only rocks pushed through extreme metamorphic cycles retain Kornerupine. Only pegmatites with the right chemistry intersect those cycles. And only a handful of terrains around the world host both. Kornerupine's muted glow tells of fire that never touched the surface, of pressures that sculpted continents, of mineral pathways still incompletely mapped. To the untrained eye, it is a subdued stone. To those who read Genesis as geology's autobiography, it is the chapter heading of a story not yet concluded. As Kornerupine steps aside, its trajectory points toward a mineral of revelation, Chrysocolla, whose gem silica form speaks softly of copper systems vast enough to reshape economies. Ranked 5th, Chrysocolla, the fragile blue threshold born from the Earth's deepest sacrifices. The story begins in copper deposits, massive systems born when volcanic fluids forced their way through shattered rock, saturating it with metal. These systems run hot. They burn through the crust. They reshape entire landscapes. And in the final stages of their evolution, when the fluids cool and the copper oxidizes, Chrysocolla forms in thin, fragile skins. These skins are not the treasure. They are the boundary, the narrow rim between a deposit exhausted at the surface and the deeper architecture where value still sleeps. But the rarest form of Chrysocolla tells a different tale. When silica-rich water rises through these oxidized zones and infiltrates the soft mineral, it begins a slow, patient replacement. Molecules of silica enter, crowding out the copper-bearing mass grain by grain. Over time, the stone hardens into a translucent blue-green glass. Gem silica, the most vivid, most saturated cousin of Chrysocolla, and one of the most expensive silicate-based gems the Earth can produce. To create a few centimeters of gem silica, a copper system must endure decay, collapse, oxidation, infiltration, replacement. It is a transformation paid for in geological scars, and for those who seek it, the price can be equally steep. Across Arizona's desert plateaus and Peru's quebradas, in the desolate belts of the Congo and Namibia, gem silica zones sit at the interface of abandoned copper workings and unstable ground. Old haul roads collapse without warning. Tunnels gas with heat. Dust rises from tailings that still carry the memory of heavy metals. In places where gem silica has surfaced, miners have spoken of pits caving in under moonlight, of shafts sealed by landslides before anyone could descend, of veins mapped but never reached. Yet the stone continues to draw them back. Exploration companies, artisanal miners, private geologists, they all know the rule. Where gem silica forms, copper systems of immense scale lie beneath. And with copper set to dominate global energy transitions, from electric grids to battery networks, the value of these systems grows faster than the gemstones themselves. What Chrysocolla signals from the surface is not just the end of a cycle, but the beginning of one. Beneath the fragile blue lies or that could reshape regional economies. The sacrifice extends further still. In some regions, ancient groundwater must be drained to access the deeper veins. Elsewhere, miners must negotiate with landscapes marked by pollution from earlier eras of extraction. And in a few places, the land itself has already paid. Hills hollowed out, riverbeds discolored, vegetation thinned by the breath of smelters long retired. Chrysocolla therefore stands as a paradox, a soft mineral formed from collapse, whispering of wealth concealed in the ruins beneath. A stone so delicate that it breaks under touch, yet tied to deposits strong enough to drive nations forward. Its gem silica form glows like tropical water, but the ground that creates it often bears the weight of decades, sometimes centuries of human endeavor and environmental cost. As the blue-green mineral recedes into shadow, its message remains. Every treasure has a threshold, and every threshold demands something in return. From this place of sacrifice, the countdown ascends toward a mineral shaped not by collapse but by revelation. Enstatite, the mantle-born clue to diamond-bearing depths. Ranked fourth, Enstatite, the mantle-born precision stone, mapping the hidden pathways of kimberlite depths. Enstatite is a crystal of thresholds. It forms only when magnesium-rich silicate melts cool within an exceptionally narrow thermal window between 900 degrees Celsius and 1,200 degrees Celsius under pressures that mimic tectonic roots. Any deviation, too much iron, too little silica, a cooling curve even subtly misaligned, and the lattice reorganizes into other minerals, hypersthene, bronzite, or olivine. But when the conditions lock into place with surgical exactness, Enstatite emerges as a perfect record of the mantle's pulse. Because of this precision, Enstatite becomes a geological instrument. Wherever it surfaces, carried upward in volcanic conduits, trapped in xenoliths, or woven into the veins of ultramafic belts, it offers coordinates. Its iron-magnesium ratios map the depth at which the host rock equilibrated. Its exsolution lamellae mark the cooling rate of mantle material rising through the lithosphere. Its optical properties shift subtly depending on the pressures it endured. Scientists read these clues the way astronomers read starlight. But for gemstone exploration, Enstatite signals something more valuable than mantle history: the proximity of kimberlite-bearing systems. Kimberlites, the volcanic pipes that sometimes carry diamonds to the surface, intrude rapidly through the mantle. In their ascent, they tear fragments from deep rocks, pieces of peridotite, pyroxenite, and eclogite. Enstatite often survives this violent journey, arriving near the surface as grains, streaks, or crystalline ghosts trapped inside mantle's xenoliths. Its presence does not guarantee diamonds, but its absence almost always negates them. In regions of Botswana, Canada, and Siberia, early exploration teams mapped Enstatite-bearing xenoliths long before drilling rigs arrived. These fragile markers, small enough to slip through one's fingers, guided multi-million-dollar exploration programs. Some of the world's most productive diamond pipes were first detected not through geophysical anomalies, but through the precise chemical fingerprints of enstatite scattered across riverbeds. Ranked fourth, Enstatite, the mantle-borne precision stone, mapping the hidden pathways of kimberlite depths. Enstatite is a crystal of thresholds. It forms only when magnesium-rich silicate melts cool within an exceptionally narrow thermal window between 900 degrees Celsius and 1,200 degrees Celsius under pressures that mimic tectonic roots. Any deviation, too much iron, too little silica, a cooling curve even subtly misaligned, and the lattice reorganizes into other minerals, hypersthene, bronzite, or olivine. But when the conditions lock into place with surgical exactness, Enstatite emerges as a perfect record of the mantle's pulse. Because of this precision, Enstatite becomes a geological instrument. Wherever it surfaces, carried upward in volcanic conduits, trapped in xenoliths, or woven into the veins of ultramafic belts, it offers coordinates. Its iron-magnesium ratios map the depth at which the host rock equilibrated. Its exsolution lamellae mark the cooling rate of mantle material rising through the lithosphere. Its optical properties shift subtly depending on the pressures it endured. Scientists read these clues the way astronomers read starlight. But for gemstone exploration, Enstatite signals something more valuable than mantle history: the proximity of kimberlite-bearing systems. Kimberlites, the volcanic pipes that sometimes carry diamonds to the surface, intrude rapidly through the mantle. In their ascent, they tear fragments from deep rocks, pieces of peridotite, pyroxenite, and eclogite. Enstatite often survives this violent journey, arriving near the surface as grains, streaks, or crystalline ghosts trapped inside mantle's xenoliths. Its presence does not guarantee diamonds, but its absence almost always negates them. In regions of Botswana, Canada, and Siberia, early exploration teams mapped Enstatite-bearing xenoliths long before drilling rigs arrived. These fragile markers, small enough to slip through one's fingers, guided multi-million-dollar exploration programs. Some of the world's most productive diamond pipes were first detected not through geophysical anomalies, but through the precise chemical fingerprints of enstatite scattered across riverbeds. Ranked third, Clinohumite, the amber signal revealing the mantle pathways hidden beneath ancient cratons. Deep beneath mountain roots, below the layers shaped by weather, rivers, ice, and human memory, lies a realm few minerals can speak for. It is a world of ultramafic pressures, of mantle fragments rising through violent conduits, of rock that formed before the continents themselves were assembled. In this hidden architecture, Clinohumite is a quiet emissary. At the surface, it rarely impresses. Warm amber to burnt orange, sometimes brownish gold, sometimes almost dull. Collectors often overlook it, assuming it is a byproduct of peridot-rich terrain, a curiosity rather than a clue. But in the places where Clinohumite appears, the earth is telling a deeper story. Clinohumite does not form casually. It is born from the reworking of olivine, the mantle's most abundant mineral, when boron-bearing fluids infiltrate peridotite at extreme temperatures. This requires a sequence of events so specific that geologists once considered the mineral almost anomalous, confined to only a handful of known localities. But as mapping improved, fragments of clinohumite were found in unexpected contexts. Xenoliths carried upward by volcanic pipes, altered mantle nodules in ancient cratons, and metamorphic zones forged under pressures almost too intense for crystal survival. Each fragment was a revelation, not of the clinohumite itself, but of the environment it came from. Where clinohumite occurs, the subsurface often hides the contact zones where peridotite, volatile-rich fluids, and tectonic deformation meet. These zones are exactly where diamond-bearing kimberlites originate, deep, violent, and rare. They are also the corridors that host magnesium-rich silicates, platinum-group metals, and the deep roots of ancient cratons, terrains that remain some of the least explored, yet most valuable, on Earth. In northern Tajikistan, tiny grains of clinohumite embedded in metamorphic marble led researchers to identify a subsurface peridotite body previously unknown. Later surveys revealed a deeper structure, a mantle slice uplifted by continental collision, that may still conceal untested kimberlite pipes. In Canada's Shield, clinohumite-bearing xenoliths emerging in glacial till reshaped exploration models, pushing drilling operations kilometers west of their initial targets. And in Tanzania's Umba Valley, clinohumite appeared in float material years before anyone realized there were undiscovered ultramafic intrusions under the foothills. Clinohumite becomes revelation because it is out of place at the surface. Its presence means something was pushed upward, a sliver of mantle, a fragment of deep-time geology, a hint of roots older than the landscapes above. To explorers, clinohumite is not simply a mineral. It is a sign that the crust has been breached, that mantle material has risen close enough to touch air, that the architecture beneath the region is far more complex and far more promising than surface minerals imply. Its amber glow is the after-image of a journey from depths where temperatures exceed 1,000 degrees Celsius, where olivine transforms under boron-rich fluids into something rarer, something that remembers pressure long after the host rock fractures. Through clinohumite, the mantle speaks, not loudly, not dramatically, but with a precision that changes the direction of exploration. A few grams of it can redirect drilling campaigns worth millions. A single outcrop can redefine a region's geological map. It is revelation distilled into mineral form, a small, quiet stone that exposes the truth of what lies below. And as its chapter closes, the countdown nears its final threshold. Taaffeite, a mineral whose very existence reshaped the boundaries of what gemologists thought possible. Ranks second, Taaffeite, the lavender trace that fuels a global obsession for impossible gem origins. There are minerals so rare that collectors learn their names only once in a lifetime. Taaffeite is rarer still. Known originally from a single misidentified gem, Taaffeite entered the world of mineralogy like a whispered mistake, a stone that should have been spinel, but was not. Its structure, its birefringence, its chemistry, nothing matched what it visually resembled. It looked familiar, yet belonged to a category of its own. That paradox ignited a global obsession. But the Taaffeite that drives exploration does not shine. It is not the clean, lavender gem that auction houses guard with gloves. Instead, it is its low-grade relatives. The soft lilac smudges in marble, the faint violet threads in metamorphic belts, the barely noticeable crystals tucked inside pegmatitic rubble. These muted versions are the breadcrumbs that trace the edges of geological systems capable of producing the real treasure. Rare pegmatites where Taaffeite, spinel, chrysoberyl, and beryl converge under impossible conditions. Because Taaffeite should not exist easily, it requires a perfect storm of boron, magnesium, and beryllium, three elements that rarely meet, let alone bond into a coherent mineral lattice. And even when they do, the temperature window is razor thin. A few degrees too hot, and the chemistry collapses into spinel. A few degrees too cool, and the structure fails entirely. For the high-grade gem, the conditions narrow even further, like threading a needle inside a moving mountain. This improbability is the engine of the obsession. Across Sri Lanka's metamorphic highlands, miners search stream beds for pale lilac pebbles. Not Taaffeite itself, but its less perfect kin. In Madagascar's pegmatite fields, Geologists log samples with lavender hues in notebooks more carefully than they mark rubellite or aquamarine. In Tanzania, artisanal diggers have learned to recognize the dull, chalky variant. They keep it not for sale, but as a signpost, a direction marker pointing deeper into zones where fluid chemistry once danced on the edge of chaos. For exploration firms, these low-grade Taaffeite zones are worth more than their weight suggests. They map reaction fronts, pressure thresholds, fluid pathways, the invisible boundaries that define where beryllium-rich pegmatites may branch, where spinel-bearing marbles tighten into pockets, where rare mineralization concentrates for reasons still not fully understood. Entire research teams build models around the faint lavender stains of low-grade Taaffeite. They analyze trace elements. They reconstruct metamorphic gradients. They chase clues across terrains once dismissed, and each time the pattern deepens. Where low-grade Taaffeite appears, something extraordinary has happened. A chemical convergence so unlikely that it may signal the presence of gemstone assemblages worth more per gram than platinum. In auction rooms, the finest Taaffeite gems trade hands quietly, privately, for sums that escape the public record. Their scarcity warps the market. Their existence fuels legend. And every time a new lavender pebble, no matter how dull, surfaces in the field, the old obsession sharpens. Could this be another doorway? Another system? Another chance at a mineral that should not exist? Taaffeite is not simply rare. It is a disturbance in the order of things. A reminder that under the right pressures, the Earth can produce something both fragile and impossible. As the documentary steps past this penultimate stone, the world of quiet obsessions gives way to the final chapter, an ending written in absence, silence, and the faintest trace of what once was, Painite. In first place, Painite, the silent mineral, marking the vanished pathways of Earth's rarest geological events. Painite arrives as a shadow, small, brick red, often fractured, often mistaken for something else. For decades, it was known from single specimens, then a handful more. Not enough to form a market, not enough to form a story, just enough to form a question. How can something so chemically improbable exist at all? Even now, its presence is quieter than any other stone in this documentary. It appears not as gem-grade crystals, but as low-grade grains embedded in muted metamorphic rock. Barely violet, barely red. You could step over it without noticing. Many have. And yet, where Painite exists, the landscape seems to fall still. In the metamorphic belts of Myanmar, Painite does not mark abundance. It marks interruption. Its low-grade forms linger at the edges of geological environments where fluids once moved with unusual chemistry. Boron-rich, zirconium-bearing, layered with elements that rarely meet in the same chamber. Something happened there, something unrepeatable, and whatever that event was, it has long since ended. Painite is the residue of an absence. To find it is to trace the outline of a process that no longer occurs, a vanished pressure regime, a cooled system that will not heat again, a corridor of metamorphism that reached its peak millions of years before any witness existed. What remains is a quiet scar, a reminder of a deep earth choreography that has already closed its curtain. Explorers do not follow Painite the way they follow ruby indicators or rare earth tracers. They follow the silence around it, the torn seams of peridotite pushed upward, the ghosted pegmatites whose fluid pathways have dried out, the narrow bands of boron-rich marble that suggest a once-living system now dormant. Painite is the punctuation mark at the end of a geological sentence. Tiny, dense, definitive. In places where low-grade Painite appears, geologists often pause, not because the mineral itself offers economic promise. Its true value lies in rarity far beyond commercial scale, but because it reveals the boundary of a vanished pegmatite province. These boundaries, though cold now, were once flush with incompatible elements, the kind that form topaz, zircon, beryl, and rare barat species found nowhere else on Earth. Many of these minerals, if still present, lie deeper in pockets that early miners never reached, pockets that modern surveys have just begun to model. Painite sketches their absence with surprising clarity. Every fracture in the host rock hints at old pathways. Every trace element maps a migration long over. Every muted crystal stands as testimony that the Earth once held conditions so precise they may never occur again. And so the mineral becomes a guide, not toward heat or pressure or wealth, but toward the edges of a geological memory. It is the stone that points not to what is, but to what was, a fossil of a chemical moment too rare to rebuild. Painite teaches in silence that some of Earth's most extraordinary formations are defined not by what remains, but by what has already slipped beyond reach. That billion-dollar discoveries may lie buried not in the presence of familiar minerals, but in the voids and gaps they leave behind. That in the absence of noise there is direction. As the countdown ends, Painite stands alone, not as the prize but as the final threshold, a low-grade mineral, easily overlooked, quietly revealing the shape of an ancient system whose richest chapters may still wait beneath untouched stone. And from that silence, the story returns to the viewer, with a question only they can answer. In a world where the rarest clues whisper instead of shine, which of these 15 stones do you believe holds the next great discovery still locked beneath our feet? In the end, these 15 overlooked stones remind us that the Earth rarely reveals its wealth through brilliance. Its greatest clues often hide in muted colors, in fractured seams, in minerals so ordinary they vanish into the landscape unless someone knows how to read them. Each stone in this journey marked a threshold, a boundary between the world we see and the vast architecture of value still sleeping below our feet. Some pointed toward ancient jade corridors. Others traced the outlines of vanished pegmatite provinces. A few whispered of forgotten volcanic fires or mantle fragments carried upward in violent ascent. And the final stone, quiet, faint, almost absent, showed that even the smallest mineral can expose the shadow of a billion-dollar discovery waiting somewhere in the dark. But the deeper truth belongs to the viewer. If the Earth speaks loudest through the stones we ignore, then which overlooked mineral do you believe holds the next breakthrough? The one clue explorers haven't recognized yet? Haija kao tra loijo bat jiao kuak tra chuyan.